Hello, here's another couple of questions on nuclear physics, particle physics, radioactivity, maybe a few other bits thrown in. Starting here by explaining what is meant by the binding energy of a nucleus. Now, I've been through this on quite a few previous videos because it does sometimes cause a stumbling block for people. Binding energy is the energy to separate all nucleons to infinity, using the language of potential energy. So it's that energy required to separate the protons and neutrons in a nucleus, so that there's no potential energy left in that system of nucleons. So that's binding energy. Part B, the fusion of protons occurs in a star when the temperature within the core is greater than about 10 to the 7 Kelvin. It takes a fusion of 4 protons to form helium-4, proton-proton cycle. Yes, energy is released because of mass defects. Right, net energy released in producing a single helium-4 nucleus is that amount, so not a lot, but there are a lot of atoms kicking around in stars. Calculate the binding energy per nucleon of the helium-4 nucleus. Right, so well, that's the binding energy, because we're taking these protons, which are considered to be at infinity, and the energy released when they bind is this binding energy. So that's what's come out. That's the net energy released in those 4 protons coming together and producing this helium-4 nucleus. So binding energy per nucleon is just that divided by 4. So 4.53 divided by 4 is going to be about 1.13 times 10 to the, minus 12. So that is joules per nucleon. Yep. C, the fusion of helium nuclei to make heavier elements occurs in red giants at temperatures above 10 to the 8 Kelvin. Right, so we've gone up by an order of magnitude. Explain why fusion of helium requires higher temperatures than the fusion of hydrogen, i.e. the protons. Right, well, we've now got a higher repulsion. So we still need to get to the same sort of range. We still need to get the strong force kicking in. So we still need to get these nuclei very close to each other. But now we've got a much higher repulsion because we've got more charge in these helium nuclei. So we've doubled up the charge there. In each one of them. So we're going to have 4 times the force, which means we're going to need more energy in order to get those helium nuclei close enough together in order to fuse, which is why we need a higher temperature. So it just follows that chain all the way through. D, estimate the mean speed of helium nuclei at a temperature of 10 to the 8 Kelvin. Right, this is something that I haven't covered in all my videos yet, but if you've done some work on ideal gases, then you will know that the average energy of a molecule, or a particle, I should say, in a gas is 3/2 kT, where K is the Boltzmann constant. So that will be equal to half mv squared, because we're saying, well, all of that energy is in the form of kinetic energy. So we just need to rearrange this and then solve. So we're going to have that V is the square root of 3 times the Boltzmann constant, which is 1.38 times 10 to the minus 23. Then we need to multiply by the temperature, which is 10 to the 8. And we need to divide by the mass of the helium nucleus, which they've given us, 6.6 times 10 to the minus 27. Okay, so, well, we've got, what have we got here in terms of powers? We've got a 10 to the 12, so we're going to have a 10 to the 6, and then multiplied by the square root of this 3 times 1.38 over 6.6. So we're going to end up with an answer which is in the 10 to the 5s. Tapping that into calculator, 4.14 divided by 6.6 square root, 0.92 times 10 to the 5 meters per second. So there you go. Yeah, fairly straightforward sort of question, that one. Now we've got deuterium and tritium are isotopes of hydrogen. So we're just adding in 1 or 2 extra neutrons. State 2 features common to all isotopes of hydrogen. Right, okay, well they've all got 1 proton. We can say that for sure, otherwise they wouldn't be hydrogen at all. And we can say that they've got 1 electron in their neutral state. So let's go with that. Explain why the total mass of the individual nucleons of a deuterium nucleus is different from the mass of the deuterium nucleus. Right, so this is the binding energy. So we want to make a mention of binding energy. And that is then the difference in what the mass is, equals the mass difference. So if you recall, again, we're always talking about binding energy. It came up on the last question as well. So as these nucleons are binding together, they then have less energy in the bound state. So that means that they've got then a lower mass. That is the mass defect because the energy has the mass. So yeah, you get a mass difference, which is that energy difference. And if you want to then separate it, this is what's going on in all of this stuff to do with fusion and fission, is you're changing around the binding energy in these atoms. You're making them more stable. And if they're more stable, there's less energy inside the nucleus, and that energy has been released in the process of either fusion or fission. Part B, we're now on to fusion reaction here between 2 nuclei. We've got deuterium and a tritium going to helium and a neutron. Neutron inside a nucleus is stable. However, a free neutron, when outside the nucleus, undergoes beta decay in about half-life of 11 minutes. Complete the decay equation for a free neutron. Okay, well, it's got to go to a proton. So we've got a 1-1 there, so that's made everything add up. And then we need a neutrino, which is going to be the anti-neutrino, anti-electron neutrino. This is this is beta decay, essentially. We've spat out this electron here, increased the proton number, and removed the excess neutron. Explain what is meant by the half-life of a free neutron. Right, half-life is the average time for half of the neutrons in a sample to decay. So you want to, excuse me, you want to mention average time and half and sample. So you want to get all of those words in to your answer there. C, for the fusion reaction to occur, the separation between deuterium and tritium nuclei must be less than 10 to the minus 14 meters. This means that the average kinetic energy of these hydrogen nuclei needs to be about 70 keV. Energy released is 18 MeV. So that's not bad because we're getting extra energy out. Calculate the repulsive electrical force between the deuterium and tritium nuclei at that separation. Right, again, this is something I haven't actually covered in my videos yet, but if you've been looking at electrical forces, then you'll know that it's product of the charges divided by 4 pi epsilon 0 r squared. So we're going to have 1.6 times 10 to the 19 squared on the top because they both got single protons. So that's 2.56 times 10 to the minus 38 divided by 4 pi times permittivity of free space, which is 8.85 times 10 to the minus 12, and then multiplied by r squared, which is going to be 10 to the minus 28. So let's deal with all of these powers of 10. So we're going to have 100 popping out when we get rid of all of those. So now we just need to type in what's left on all of this with the little numbers which I'm typing into the calculator at the moment, and then multiply that by 100 and we get 2.3 newtons. Right, that's that one. Assume that a mixture of these hydrogen nuclei behaves as an ideal gas. Estimate the temperature of the mixture of nuclei required for this fusion reaction. Okay, so we need, what did it say? It was 70 keV. So this 70 keV, so that's 70 times 10 to the 3 times 1.6 times 10 to the minus 19. That's the energy that we need on average for each of these nuclei. So that's got to be equal to our 3/2 kT. So 3/2 multiplied by 1.38 times 10 to the minus 23 multiplied by T. So let's solve that for T, which is going to come out quite high. So we've got a 10 to the 4 there, so that becomes 10 to the 7, then 10 to the 8 with all of that. So what we left with, T is going to be 14 times 1.6 times 10 to the 8 divided by 3 times 1.38. Putting all of that in, we get 5.4 times 10 to the 8 Kelvin. In practice, fusion occurs at a much lower temperature. Suggest the reason why. Right, well, this is just the average energy for that temperature. So we've got a distribution, assuming they're behaving like an ideal gas, which is what we've said there. Then you've got a range here of energies for the particles. So there's this is just the average energy. So you can say here that the average energy for temperature of this for this is 70 keV. So some nuclei will have more energy than this. Will have more energy, which will be enough energy to then fuse. Right, calculate the change in mass in a single fusion reaction. Right, so what are we getting? We're getting right, that's our energy release. So 18 times 10 to the 6 times 1.6 times 10 to the minus 19. That is our energy release. And that is going to be equal to, that's our mc squared, or our delta M times c squared. So we just need to divide this right-hand side by 9 times 10 to the 16. And then we're going to get our answer. So actually that's going to come out quite nicely because we're going to get a 2 there. So we're going to have 3.2 times 10 to the, what we got, 16 minus 35 minus 29 kilograms. So that's just using our E equals mc squared. Figure 3.1 shows the variation of probability of fusion reaction with temperature for deuterium and tritium and for deuterium and helium. Okay, right. Suggests why the probability of reaction at a given temperature is smaller for deuterium and helium. Right, because there's a greater electrical force, repulsive electrical force, because of the higher charge of the helium nucleus. Because well, I won't bother writing it out, I'll run out of space. But yeah, greater repulsive electrical force because of the higher charge of the helium nucleus. So yeah, that's covering a lot of ground, that question. It's all the same old stuff really with the all of these questions with fusion and fission. Then once you've got binding energy clear in your mind about what's exactly going on here, then everything's fine. Like I say, you've got these particles, if they fuse together, here we're saying they've got no potential energy. You fuse them together, they've now got negative potential energy. So that difference has been released. That's our conservation of energy there. So you get a release of energy. That's what's happening with fusion, and with fission is much the same thing. You've got some amount of negative potential energy. You then split that nucleus so that the products are more tightly bound. So it's more negative, and that difference is then released, which is that difference is smaller than what you're getting in the fusion case. But that's what you need to get clear in your head about nuclear reactions and why we're getting energy release.